Hello, and welcome to the second lecture in our class about mapping, images and structure. So this week we're going to talk about how dipping structure and topography interact to cause outcrop patterns, which is what is recorded in geological maps. So the crucial thing here is to understand that we have two three-dimensional surfaces that are interacting with one another. One of them is the geology, where we have surfaces that separate different rock units, and we also have topography, the shape of the landform, and we see the rocks, of course, where they come into contact with the land. And we're going to be learning how we can use structure contours combined with topographic maps to understand the outcrop patterns and what that means about the geology of the subsurface. And in particular, I want us to be able to learn how to start to draw cross sections. So, as I mentioned, geological maps are essentially the representation of a series of surfaces. And what we see on a geological map is the outcrop patterns, where the rocks would be sticking out on the surface, either because they are outcropping or because they're maybe just covered with a little bit of recent sediment. And we want to understand how those geological surfaces that describe the solid earth structure, how those interact with the topography. Where does the dipping beds or igneous bodies or faults, where do they intersect with the topography? And this is slightly complicated because outcrop patterns can be produced in a number of ways, and so when we look at a pattern on the map, we have to also look at the topography in order to understand the deep earth structure. So, for example, while flat-bedded sediments, you can imagine that those would always be at the same level, so therefore their contacts are parallel to topography. And in stark contrast, of course, vertically dipping things cut right across the landscape, and they intersect at high angle any topographic contours. So let's think a little bit about outcrop patterns and the concept of structure contours, which is what you're going to be using for a lot in the next few weeks. So a structure contour is a way we use to describe the shape of a geological surface in 3 dimensions, and it works just like any other contours. I'm sure many of you are familiar with topographic contours on maps like Ordnance Survey maps we have here in the UK, and there are other things that can be contoured. Atmospheric pressure, for example, you may have seen on weather websites maps like this that are showing the pressure of low and high pressure systems across the North Atlantic region. And we can also look at temperature through contours as well. This is an average temperature for different parts of the globe, and you can see here how they've used contours to show where's hot and where's cold. And so essentially that's really how structure contours also work. The blue surface that you see there represents a dipping surface. So, for example, the boundary between one rock unit and another one. And we can use contours to describe how it's dipping and what its orientation is like, just in the same way that you do for weather or topography. And what this really means is, of course, that on a dipping surface, the depth or the height of the geological surface is described by contours, but those contours must, of course, be flat, must be horizontal. They're always at the same height. And what this really means also is that they are always parallel to the strike of the bed. So if you see a structure contour, you know that what the strike of the bed is, and then the value of the contour will tell you which way is downhill, down dip. So an example, I see a few examples here now, so that like the top two, these show a series of 10-meter contours, The ones on the left here are widely spaced, and that tells us that the dip is quite shallow. In contrast, here we have a much steeper dip. It's a regular dip, always the same angle, because the contours are equally spaced, so we know that it's sloping down to the right in this particular case. And then of course the world is not always quite so uniform, so in this bottom example here you can see how the contour spacing is changing, and we know that that therefore means that it's getting steeper or shallower to the left, steeper to the right. And if you construct some structure contours, you'll be able to make this sort of prediction yourself. So again, here are some examples of that. Imagine this is on a map that you're going to be working on. So these are 10-meter contours. Maybe they show the height above mean sea level, for example, of a bed, or maybe an igneous body or a fault. So it's dipping down to the right because 10 meters is on the right, 100 meters is on the left, so it's high on the left, low on the right. And we can use the spacing between the contours, that distance A that you see there, to be able to calculate the dip on the bed. So we know that vertically, for example, that the opposite value here is 10 meters. It's a 10-meter difference. And if we know the horizontal spacing between the contours, we can calculate the dip, in this case theta, using a simple tangent sum. And of course, if they're packed together like this with very densely spaced and close together, it means that, just like a topographic map, it means that it's dipping very steeply. And likewise here, right? This one is steep on the left and shallower on the right. It's a fold. And here's another example. This is really a complete fold where we have the deepest values, 60 in the middle there, and the shallowest values, 10 on either side, which means it's some sort of it means it's a sort of an arch shape where the middle of the map has the surface at a high elevation and the edges are at low elevation, so it's a sort of a dome type structure. So if you understand that, we can start to try and see how these different units might interact with topography. So this is an example here where we have 3 different surfaces that are outcropping here on a map, and you can see that the light blue lines here indicate the topography. And in each of these particular locations here where the spots are shown, we can see where that particular surface outcrops. So each of these lines represent the exposure of a geological contact. And if we know where the structure contours are, we can predict where the sediment would be outcropping. For example, these 2 green ones here, it's pretty likely that it would be outcropping in the middle here too. And the way we do this, I'll show you here. Here is a dipping to the left at about 30 degrees here. And so what we're going to do is draw structure contours on here. So again, if we know that that's a 30-degree dip, and the structure contours we want to construct are at 10-meter intervals, it means that we can easily calculate what the spacing would be. So we can go ahead and do that. And we put them down there, so it's smaller numbers on the left because it's dipping. The little tick sign here shows the direction of dipping away to the left. And you can see each of the values of the structure contours, 20, 30, 40, 50, and so on. So if we then see where these intersect the topographic contours, so these 2 dots here show where the 50 meter contour reaches the 50-meter topography, right? And likewise here, this is where the 60-meter contour reaches the 60-meter topography. And so each of these little red dots indicate where that particular surface is outcropping at the surface. It's not present over here. So what you can see by joining those up, that gives us an impression about what the outcrop pattern would be for that particular surface. And of course you can repeat this with the next unit, the next boundary that we want to put in. This one has different values, of course, because it is at a different height. So this particular example has manufactured it so that the contours for each of these two surfaces sit on top of one another, but they're not the same value. You can see here this is 30, the previous one was 20. And you can also see why it doesn't outcrop, because these are, the previous one was 20 along here, and this is the 30-meter contour, which means that surface was in the subsurface. The green one, however, this is the 30-meter contour for green, and it is outcropping over here. And again, we can join them up to try and form an outcrop pattern. You'll see that because the contours are getting smaller towards the left, it means that the whole sequence is dipping towards the left. And we can do it again with another unit here. We can put in blue. These ones are higher up. I'm sorry, they're lower down. Right, they're lower down. These are deeper. And again, here we see the blue one here. So when the 70 contour meets the 70 part of the topography, that's where we have an outcrop. And so on. So it's relatively straightforward. You can imagine these are three-dimensional sloping surfaces. They're not folded, they're just flat, and they all appear to be dipping away to the left. In the case of the blue ones, these are offset. You can see those don't sit on top of one another, and in the real world they generally don't sit on top of one another. But in many of the exercises you're going to be doing, they will, just to save space and be a little more simple for you. So let's think about how structure contours can help on a field map. So for example, here we have an outcrop pattern that you can see. Again, the blue is the topography and the black is the outcrop pattern of each particular surface. We have 3 here. You see there's a hill that's 60 meters going down to 40 here. So here we have an outcrop pattern across a hill, and if we see, we can draw the structure contours where these surfaces cross the topography contours. So like the blue one here, it's touching the 40 there and 40 there. It's cutting 50 here and 50 there. And likewise for the others. Each surface will have their own contours. So if we know where the 50 and 50 blue contour is, we can draw a line through that. And we can then label that. Okay, so as it happens, the 50 blue contour is also the red 40 contour, and it's also the green 30 contour. So again, we can use that separation of the vertical separation of the contours and the vertical, which is we know to be 10, we've defined it as 10, to calculate the dip here using a simple tangent calculation. So we begin to understand therefore that this is a sequence which is again dipping towards the north, off the north slope of this particular hill. And we did that, you can see, by joining up 2 points on a single surface that cut the same topographic contour twice. We joined this one and this one, we joined this little red one with that little red one, and so on. So, of course, in some situations we don't have the chance to have 2 points. For example, here, this is a series of contours going from 70 to 10, and we have a surface that outcrops here, but it doesn't cut any of the contours twice. So what can we do if we have a situation like that? Well, we have the individual, the single points, right? The 60, 50, 40. But what we can do is to draw ourselves a little 3-point problem here. So essentially, point A is at 20, point B is at 30, and point C is at 40. So if we join the 20 and the 40 with a different line, the midpoint of the 20 and 40 must be at 30. Like that. And now we have two 30 contour points, and we can draw a line through those. The one that actually outcrops and the one that we have inferred by joining the two. And once you have one, of course, all the other contours have to be parallel to that. So we're able then to draw in all the other ones based on our simple assumption that this surface is dipping in a regular fashion and is not folded. Of course, that's not always true. We do know that when you do have folded sequences, that the numbers will reverse and the spacing on the contours will change through time, and so we just have to be careful to look out for that when we're dealing with a map. So fortunately, there are some simple rules of thumb that you can use to try and understand the geometry of rocks in the subsurface by using their outcrop patterns. So that you've seen the basic principles. The outcrop occurs when the surface structure contour cuts the topographic contour. So there is this thing that geologists like to call the rule of V's, and it gives you some very simple guidance about which way units must be dipping that you can just see on the map. So for example, this appears to be well, it is a V, isn't it? It's an outcrop pattern as a V, but you can also see that this grey unit is parallel to the topographic contours. It doesn't go up or down the hill, right? So we have a valley here in the topography, and we have this outcrop pattern, which on the map looks like a V, but we can also see that it's essentially flat. It has to be flat, otherwise it wouldn't be parallel to the topographic contours. If, however, we have the beds are dipping upstream like this, you can see that there's a different sort of pattern. They are cutting the contours, and because the rock is dipping to the upper right and the valley is dipping to the upper left, we have a very subdued V-type shape. So we do know that it is dipping up the topography and not down topography. So, as I mentioned, vertical features, of course, cut straight across everything. They're just flat on the map, and that's a really simple case. Anything that cuts right across the map, crossing contours, you know it has to be vertical or very steep. We already saw that one. So if the unit is dipping, however, down the valley, again, the valley here is dipping towards the bottom left here, and if our geological unit is dipping in the same direction, then we get a really enhanced V-type shape, right? Not the suppressed one we had when the rock was dipping in the opposite direction from the topography. And then this one again, so this one is dipping down. In this case, it is dipping at the same value as the slope, as the valley itself is dipping. So the center of this stream here, imagine a stream running in the middle of this valley. You can see the valley is dipping to the bottom left. The rock itself is also following that because it's parallel. You see, these are, it looks just like a grey strip, which it wouldn't do if the dip was not the same as the topographic dip. And again, this is another example where the stratigraphy, the rocks, the sedimentary rocks, are dipping down valley in the same direction as the topography, but in this case quite steeply so. The flatter ones had a much more accentuated V shape to that. And you'll get used to seeing these patterns when you look at both the fantasy geological maps we're going to practice with, but also of course real geological maps that we start to look at halfway through the term. So when we look at a geological map, we want to know something about what the dip of each unit is, and we often want to know how thick each geological unit is. So there are these differences between true thickness, vertical thickness, and the outcrop width. Those are three important different things. So the true thickness is the perpendicular distance between the bottom and the top of each unit. The vertical distance is, well, exactly as it says, measuring vertically through the unit as though you were drilling it. And the third concept is the outcrop width, so that represents the width on the map of the distance between the bottom and the top. Let me show you some examples. So these here show the outcrop width, right? So in this one is steep dipping, so it has a smaller outcrop width. The shallower, if the topography is flat, then the shallower the dip is, then the wider is the outcrop. And you can see that this width is different actually from the thickness of the bed. So these two here have the same vertical true thickness, but their outcrop pattern is, their outcrop width is much different. And that simply reflects the difference in the dip. This one's steep and this one is shallow. And again, you can play this game on sort of more exciting topography when most of the time the topography of the Earth is not flat. So if we have ridges and hills here, you can see how these two beds that are very similar thickness, this one has a thin outcrop width and this one has a wide one, and that simply reflects the interaction of the bed boundaries with the topography. The true thickness is this measurement. And it's something you're going to have to learn how to calculate, but fortunately it's not very difficult. You can calculate this from either the vertical thickness, for example, if you were drilling it with a borehole, you would have measured this vertical thickness. And if you know what the dip is, then you can calculate this true thickness through a simple piece of trigonometry. Conversely, if you know the outcrop width, which is more common when you're dealing with geological maps, then again, the width and the dip allow you to calculate the true thickness with a simple sine calculation. It is worth noting that the difference between true and apparent dip, so whether the apparent dip is an outcrop or on your cross section, there you can see that if we have a sloping surface here shown in orange, the true dip is the one that runs steepest, essentially perpendicular to the structure contours, straight down dip, the steepest possible route. If you measure the dip in an oblique fashion, of course it's not as steep. Clearly if it was parallel to the structure contours it would be 0. But if you have an oblique view of the geology, you have to account for this difference between the apparent and the true dip. And fortunately, your guidebook has this very helpful table in it, a graph here that allows you to see the true dip and the apparent dip here and account for that obliquity. So if you do need to calculate to switch between apparent and true dip, you can do it using this without having to do a lot of fancy calculation. And you can do it with a little app, so you might want to use this. It's pretty straightforward. So the last thing I want to mention today are cross-sections. So geological cross-sections are at the heart of this class. I want you to be able to draw a section across a map, that if I give you a map, you can tell me what the structure in the subsurface is like. Where you draw your cross section, well, that's sort of up to you. You might, in this class, have to draw it where I ask you to do. Usually people draw it through things of interest. So here, these are folds. They're from southwest England, and the line A to A prime has been drawn sort of across those folds, usually perpendicular to the strike of the fold, so that it will show the structure nicely. And of course we want to be able to fit the section on a single piece of paper. So for example, this is an example here where we have a slope dipping from the left to the right. The topography is dipping from the left to the right, and we have three geological units, the blue, the green and the orange. And we can see here that we know something about their structure. We know that this one is dipping 10 degrees from the horizontal to the right, and over here it's dipping 10 degrees to the left. So again, we draw our cross section perpendicular against the strike of the units to show the structure as neatly as possible, and we can draw a cross section. And essentially what you can do to do this is as so. So you get your, first of all, you need a horizontal axis, and then you need a vertical axis, and it's easier for you if both of those are the same. Otherwise you may have to make corrections for vertical exaggeration. So if we look at this particular example, we can see our topographic contours, 50, 40, 30, etc. And these we can use to draw on the cross section where the land surface is along the cross section. So where it intersected the 50, the 40, the 30, and then you can just join those up, and you can see here's a very like a shallow dip across there. The next thing is to be able to put the geology on there. So here we put our cross section back on the map, and we mark out the intersections, the surfaces between the three units. This is the blue-green and over here, and this is the orange-green here. And then we can colour in what the outcrop is like. So here we have blue on either side, orange in the middle and green between the two, so that we know that this is the geology at the surface. Now we come to the subsurface. So you know that these rocks are dipping 10 degrees and 10 degrees in opposite directions, and so with your trusty compass clinometer you can mark that on. It's only 10 degrees, it's quite shallow, they are in opposite directions. You can just draw a little tick there to show the inclination, but you can then extend that. This is a very regular, simple example. So everything on the left is dipping to the right, everything on the right is dipping to the left. And so if we join these up, you can see that we have a description here of a rather shallow syncline with the slope, the topography dipping inwards, but the sedimentary rocks themselves dipping more steeply. We don't know how thick the blue unit is because we don't see the bottom of that. But we've managed to transform our map into a cross-section. And then we can extrapolate it, essentially using the structure contours to show how the beds not only extend into the subsurface, but where they would have been in the past and have then been eroded away. So I did want to emphasize the importance of making your maps and sections neat. It is quite important to do this. There are definitely marks for making your presentation as nice as possible, and to labeling things clearly. If you hand in something messy, you'll get less marks than you would as if you did something nice, and it's important to use a good color scheme. In general, I would discourage you from having vertical exaggeration. You can have vertical exaggeration, but it does mean that it's much harder if you've extended this vertically. This dip, of course, is not actually the true dip anymore, and you'll have to correct for that, which is another piece of work that maybe you don't want to do. I mean, it's not terribly complicated, but I prefer not to do it, and I recommend that you don't. So today we're going to do 3 little exercises which are in your course book. First of all, we're going to look at the rule of V's. We're going to look then at outcrop patterns and structure contours. And then we're going to look at the problem of apparent dip.